Good morning. We talked about the switching power pole, okay, as a basic building block for any power converter in which you have to connect a source of energy to a load by means of switch, which is operated by hard switching or forced commutation. Okay, the basic topology is here reported by referencing to the bipositional switch. This ideal configuration of the switch in which the node A is connected through the node 1 or 0, okay, depending on the indication of the unitary switching function QA, which is a low power digital signal that has the value 1 or 0. Okay, when 1, the node is connected to the node 1, so connected to the positive polarity of the voltage VD. When it is 0, it will connect to the node N. Some hypotheses are, say, on the basis of this circuit. The voltage VD is considered to be constant. Okay, so VD is constant. If this voltage is, let's say, has some ripple, the capacitor CD makes this voltage to be basically constant for our application. The current IA basically is not constant, but it has a very small ripple depending on the value of the inductance cell, okay? And basically this is the current pore, so we can think of having IEA as generated by a current source, basically. Okay. We found out. Also, I have to say that the switch is also ideal. Okay, so the action of this switch is totally ideal. It means that both statically it behaves like a short or an open circuit. Dynamically, the transition are from one position to the other one comes in a very fast way. Okay, they are very, very fast. Having these characteristics, we found out some instantaneous expression. For example, VINT is the same of QA T multiplied VD. The same happens for the current IDA, which is QA T multiplied IAT. Remember that for some specific conditions that are related to the function that multiplies the unitary switching Q variable in these expressions, you can instantaneously convert this instantaneous expression to average expression. Okay, so in order to do that, we have to consider that the unitary switching function is a periodic function having period Ts. Okay, and we can pass from this instantaneous expression to average expression, VAN equal to DAA multiplied VD, and IDA is DA multiplied IA average value, in which the duty cycle is simply the average value over the switching period Ts of the unitary switching function. Okay, VAN is obtained by this quantity is the average value over Ts, etc., etc. Okay, the duty cycle is a quantity that simply indicates the ratio between the time interval in which the bipositional switch is in the position 1 with respect to the total period Ts. Okay, this is T on over Ts. T on can be 0. or at the maximum can be TS. So the duty cycle ranges from 0 to 1. Okay. So the problem now is that the consequence of these, say, characteristics that we found out last week is that, as you can see, we can, let's say, we derived that the average quantities, for example, of the output voltage across the current port, or the current characteristic at the voltage port of this switching power pole, depends on the duty cycle, okay, which is the average value of the unitary switching function. Now, so we found a tool by which we can modulate, we can change the voltage at the current port or the current at the voltage port simply by changing the duty cycle, okay? In the case we had, this is not the only possibility, but most of the time is this modulation is performed in this way. When we have TS, which is constant, so the switching frequency, the frequency of the unitary switching function commanding and controlling the activity of the switch is constant, what does it mean change duty cycle? Change in duty cycle means change the width of the T-on pulse, okay? So if you think that the unitary switching function is something like this, for example, over TS, it can be I for a certain, say, interval that we can call T-on, okay? And since this is fixed, the duty cycle is something which is, let's say, can be represented by the average value. Okay, so changing the duty cycle means that I have to change the width of this pulse. Okay, if I change the width of this pulse, for example, say, enlarging it or made it narrow, I can change the duty cycle, and changing the duty cycle is the means by which I can change the average value of this characteristic. So I can modulate, I can control, I can manage this important electrical characteristic by acting on the T-on pulses, okay? So it is for this reason that all the block that generate the unitary, which are in charge to generate the unitary switching function, are called modulator. Okay, so we have here a modulator. And in this specific case, the modulator acts on the width of the pulse. Okay, so this is a pulse width modulator, okay? PWM for short. This pulse modulator generates this unitary switching function on the basis of a control voltage. Let me call this V control for the switch that I called A, okay? I will stress the fact that the name of this specific switch power pole is A, because later on during this course we can find a combination of this switching power pole in which one it can be called A, B, C, etc. So in this case there is a little bit of confusion, but this is the V control that we can have at the input of this pulse width modulator. This control is derived from direct measuring the characteristic of what you control in this switching power pole, so using a sort of, say, feedback, or maybe it can be supplied by an external, by the user on the external of the circuits, for example, in this situation which you have an open loop situation. Okay, so the control is generated by, is provided by feedback or by the user, depending on the sort of control you are considering. So let me just introduce how is this generated the unitary switching function by using this pulse width modulator. This kind of modulation is also called the natural sampling pulse width modulator. In this case, we have a circuit which is composed by a comparator, the comparator has an input at which you provide a triangular signal that we call V triangle, and at the other input you have the control voltage V control A. What is the output of this comparator? Let me put, say, graphically the behavior. Suppose, for example, you have a triangular waveform, which is something like this, is periodical function. The period of this triangular waveform is exactly Ts, okay, which is our switching period, okay, the period of the unitary switching function, okay. The peak value is called V triangle, then put this at on this quantity, and then you have the control voltage. So, okay, the control voltage is, say, for example, can be a constant voltage, V control A. Okay. The comparator compares the voltage at its input, and for example, for this specific interval, the blue curve is higher than the red curve. Okay, so it means that the control voltage is higher than the triangular voltage, and that specific situation, the output is high logic level. Let me put here 1 logic level. Okay. Then there is a interval of time in which the opposite is true. In this situation, the triangular waveform is large than the control voltage, so the output comparator voltage is, let's say, logical 0. And then it follows, there is another interval in which the control voltage is higher, and etc. So you can see here I generated exactly my rectangular waveform, okay, logical signal, 0 logical level, 1 logical level, okay, which is, say, a periodical waveform of Ts as a period, and we can use this waveform exactly as our logical unitary switching function. Of course, you know that in the bipositional switch there are 2 switches. Okay, one is the high side switch and the other one is the low side switch. Remember, A plus and A minus switch. And so for the A plus you can have the unitary switching function, which is called QA plus, which is the same of QA. For the opposite, so for the low side, we have the unitary switching function, which is the not version of the QA function. Okay, they are logically inverted in order to avoid the simultaneous conduction of both the transistors, both the switches, in order to avoid short-circuiting the input. Okay, typically Ts is fixed. Okay, as I said before, this is not the only way to do, okay, say this kind of modulation. And also the peak value of the triangular voltage here is something that is typically fixed, okay, is internally generated by the modulator, and it is a value that you should know in order to say to understand what happened in your circuit. So we can say that this modulation can be simply described by saying that when the control voltage A is larger than the triangular voltage, then the unit switching function is 1. Otherwise, the unit switching function is 0. Okay, this is the say the rule by which you can have this generation. Let me put on a plane the duty cycle, okay, that is generated by this process versus the control voltage. Okay, the control voltage in our discussion, in order to generate the unitary switching function QA, okay, the control voltage should be included in the dynamic of the triangular voltage. Okay, so what does it mean? That the control voltage cannot be less than 0, or say cannot be higher than the triangular peak. If the control voltage is something like this, okay, what happens? That you have no comparison. The unit switching function is always 1. Okay, so is, say, constant. In that case, I lose all the possibility to change, to modulate the duty cycle, so to change the, say, this width, in order to, say, control, to manage to change, modulate the output quantities, like, for example, the average value of the voltage VAN, etc. The same happens when the control voltage is less than 0. Okay, so the control voltage has the same dynamics, must have the same dynamic of the triangular voltage in order to get the benefit of this kind of modulation. Okay, so the control voltage can range from 0 to V triangular peak. What happens when the control voltage is exactly 0? Okay, so if the control voltage is exactly here, okay, the comparison provides you a QA which is always a 0. What happens if the control voltage is exactly at the triangular voltage peak? The QA is always 1. Okay, so these are the two limits. So here you have always 0, meaning that the duty cycle is 0. And here you have always 1 QA, meaning that the duty cycle is exactly 1. These are the two extreme. So if you, say, consider that the variation is, say, basically linear, okay, the duty cycle has a variation versus the control voltage applied to the input of this modulator that can be represented in this way. Okay, so in this way, also you can find that the slope of this quantity, it is dA over V control A is exactly 1 over the peak value. Okay, this is the mathematical representation of this curve. Okay, this quantity, this equation here, represent what is called the transfer function of the pulse width modulator. Okay, if you use this transfer function here, for example, let me consider this expression. This one, for example, for the average voltage at the current port, VAN average value. DIA multiplied the input constant voltage VD, but DIA is V control A over V triangular peak from our previous consideration, that we get that VAN is, let me put here the constant quantities, so VD over V peak value of the triangular voltage. Both are constant, VD for our supposition, and the peak value of the triangular voltage, because this is the case, multiplied by the V control A, which is something that you provide from your feedback or on the external side. So as you can see here, the average value depends on the product of a constant quantity and depends on the control voltage you applied on the external side. This can be also indicated by K pole multiplied V control A, where K pole is the ratio between the input source and the peak value of the triangular voltage. In these terms, you can see that here you have an amplifier, okay, because you have that the average value of the output is simply a terms, which is a constant terms, multiplied input. So you can say that from the control signal to the output average quantity, you have a sort of amplifier. It's like that is the same having a control voltage, okay, that is amplified by this amplification term, K pole, in order to get it as your output the average value of the voltage VIN. Okay, this is a sort of amplifier. Okay. Let me just to have some more details about some random consideration about this quantity. A is from 0 to 1. So that means that VAN, average value, is something that, let's say, goes from 0 to VD. So you cannot have at the output an average value which is larger than the input source. Another, say, consideration that we can make here, that I said that this is a sort of amplifier, okay, and you can have here, say, this amplifier which is made by modulating the control voltage, okay. But this kind of modulation applied to this switching power pole generates at the output voltage port VAN over T, which is, let me put here this schematic here, this voltage here, a highly distorted signal. Okay, so this process by which I can apply a control voltage here, let's say, transfer the value of the control voltage, I translate this value into a duty cycle of a unitary switching function, and then generate a VAN signal. The VAN signal is highly distorted because this is a rectangular signal here. Okay, it's something like this. So there is a very large, let's say, distortion in this process, okay, which is generated by this, say operating principle. So pulse width modulation induces the generation of a highly distorted VAN over T. Depending on the value of the unitary switching function, it can be equal to VD or it can be 0. So this is not something that you can say it is not distorted. If you look at the spectrum, so the distribution of the sinusoidal components of this waveform, you can see that you have a DC component at frequency 0, DC component that is the average value. Then you have the fundamental component at frequency Fs. Okay, and then typically you can have all the harmonics at frequency 2Fs, 3Fs, 4Fs, etc., up to infinite. Okay. Typically, this is for if the waveform is ideal, so it is exactly as I drawn here, so it has infinite steep, say, edges, etc. Then the harmonics that are the even harmonics are not appearing here. So in this situation, you have just the odd harmonics. Okay, but anyway, you can find, since this is not something that happened in practice, that you have a real waveform with, as say, finite slope edges, etc. You have all the harmonics. Okay, in the ideal case, you can have also the only the odd harmonics. But anyway, you have a highly distorted. But this kind of spectra also include the information that I need to recover. And information that I need to recover is in the average value. The average value, which has a peak value, say the value of this average quantity is exactly K pole multiply the control voltage A. Okay, this is the value of this harmonics. So in order to recover the quantity that can be modulated by using, say, K pole, so using the control voltage and using the variation of the width of the pulses in the unitary switching function, you have just to eliminate the fundamental and all the high order harmonics, and then you have just to retain the DC component, the average value. So this means that this process started by using a modulation, a pulse width modulation specifically, control voltage, which is compared with a triangular waveform. The information that is in the level of the control voltage is, let's say, employed to generate a variation of the duty cycle, a specific value of the duty cycle, which in turn induces a, say, distorted voltage waveform. And then at this point, I can use a process which is the opposite of the modulation at the beginning of this chain. So I need to demodulate the voltage waveform VIN in order just to keep the average value. Okay, so at the end of this process, in order to get the VAN average value, which is the quantity that I say applied here, I need to demodulate. Okay, so here I need a demodulator. Let me put here a block, and this block is a block at which output you can have VAN average value. Okay, so this typically what is the modulator, in which way you can extract from a say spectrum, which you have several harmonics, just the DC component. You have to use a low pass filter. Okay, so the demodulator action typically is done by using a low pass filter. Here, the inductance that I always put at the current port to force the condition that the current IA is constant or it is a piecewise linear current, just to reinforce the current source action at the current flowing through the node, can be employed in this demodulator action. Okay, so typically, so the demodulator is the block that includes also the inductance. So this is a low pass filter that acts as a demodulator. Okay. All this part here is our demodulator block, including also the inductance L. Okay, for example, if you put in this blue box here a capacitor, remember the example that I gave you about use of the switching power pole originating, say, in the step down of the buck converter. I just employed here a capacitor here. The capacitor, together with the inductance of the inductor L, induces a second order low pass filter that is exactly what I need in order to extract the average quantity from the highly distorted rectangular waveform VAN. Okay, but this can be, say, even more, say, complicated depending on what you really need. Okay, so basically the process is the process of using this control voltage at the input of the modulator to transfer the information of the control voltage into a modulation of a duty cycle here, generate highly distorted signal by using this sort of amplificator, okay, and to consider a demodulation action on this waveform to, say, extract the information I need the most, okay, which is the average value of the voltage, because this is a quantity that can be directly modulated by the control voltage. Okay, so the discussion I had here, okay, can be a little bit generalized, okay, because all the discussion that I provided to you describing this sort of operating principle started from the pulse width modulator is done by using a control voltage which is a constant quantity. Okay, but I can generalize this discussion a little bit by considering that I can also have a control voltage which is not constant. So all the analytical relationship that I found to you before can be also valid if you have something which is not exactly constant as a control voltage. Okay, so let me just put here the triangular waveform of the modulator having peak value with triangular hot. Then I have this period, and then suppose that I have something which is not constant. Okay, now my control voltage is something that changes. What happens? Okay, all the discussion is, say, is valid. For example, the comparator compares the triangular waveform with the control voltage at its input, providing you the unity switching function with the same rules. When the control voltage is higher, then the unity switching function will be 1. Otherwise, you get 0. Etc., etc. Okay. So even here you have your modulation of the duty cycle. So you can say that VAN is always given by the duty cycle. Now the duty cycle can change, say, from period to period because the voltage is not constant. So let me put explicitly the variable T, okay, like in this way, like the current, the same. Okay, average quantities. And now suppose that I have the control voltage that has a dynamic. The dynamic is the values can be assumed by the control voltage that are within the dynamic of the triangular wave, like in this way. Okay. If you have always this situation, that is the same situation I say explicitly employed before for our constant V control. Remember, I said that I need that the control voltage is always within the dynamic of the red curved triangular waveform. Okay, and so the same happens here. Now the dynamics, so that if you want the peak-to-peak value of this, say, quantity here, this is a generic, not say constant quantity. It's not periodical quantity. Okay, something that you can have variables. So you have a dynamic that say include all the possible values that you can have here is within the control, the triangular waveform. Then you can also say that VAN average value is K pole multiplied with control AT. Okay. Remember, only if the dynamic of V control A is included, so say included in the dynamic of V triangular. This situation that I illustrated twice, one for the constant control voltage and now here for this variable control voltage, is what is called the linear pulse width modulator. When you see linear pulse width modulator, means that you always exploit the possibility to compare your control voltage with the triangular voltage. And this can only be possible if the dynamic of the control voltage is included in the dynamic of the triangular wave. Okay, so this is what is called the linear. So in both the situation, I exploit the linear pulse width modulator. The linear pulse width modulator leads to this specific transfer function. Okay? This transfer function here is only valid for control voltage, which can be constant or variable, but which is in the linear region, let's say. Okay, with control voltage that can be range here is not, say, higher than the peak value of the triangular voltage, is not lower than 0. Okay, and so when you have this characteristic, then you can derive this one, okay, which is the same for both. So if you are in the linear situation, okay, you simply see that you have the same process as before. I can say transfer the information that are included inside the variation of the control voltage into the variation of the duty cycle of the unity switching function, included in the variation of the width of this variable. So the width of this unity switching function changes accordingly to that, say, the information, the variation of the control voltage. And then this quantity is amplified by the switching power pole, by this term, and then you can have the same information of the control voltage amplified by a k-pole at the output of a demodulator in terms of an average value. Okay, so as you can see here, this is a typical, let's say, process of communication, which you have modulation of the information, and then, say, the process elaboration of the information, then you can get, say, demodulation, so you can have, again, the information you get at the input side. Okay, so as you can see here, these characteristics of a communication channel that you can find out also here leads to the fact that sometimes the triangular waveform is that the control voltage is called, say, the modulating signal, and then triangular waveform is called the carrier. So sometimes you can see that in terms of, say, with the classic standard terminology of telecommunication field, you can see that the control voltage is a modulating signal, and you have a carrier. So you can, say, transfer this information into another quantities. In this case, is the width of these pulses, the variation of the duty cycle, and then you can amplify, etc., and demodulate. Sometimes you can find also this quantity. The average value I'm referring here is the, let's say, for example, dA is defined in this way. It's called the moving average. Now it requires a tau here, tau. Okay, so this is called the moving average. Is the average of the variable computed on several different, let's say, windows that as TS as width. If you look at these characteristics, you can see that basically what we are doing is a sort of discrete transformation of the information that are inside the variation of the control voltage. Let me put this concept a little bit, say, graphically. So I have the triangular waveform, the carrier signal, and then you have the control signal, the modulating signal. Then you have again the unitary switching function, which comes out for comparison. Something like this. Okay. Etc. The duty cycle is computed at each TS, for example. Okay, so it means that the duty cycle of the unitary switching function QA during the first time interval, let me say this is the first cycle, is, for example, I don't know, this one. Let me put in red. This one, okay? So this is the duty cycle level dA1 that you can have in the first cycle. Then you have another cycle, the second one, and then you have another different duty cycle, which is basically more or less the same as before. Then at the third cycle, you have a duty cycle which is a little bit higher, okay? And then in the fourth cycle, you have something which is again, say, something less. As you can see, the duty cycle computed basically follows included the same variation of the voltage, the control voltage. Okay, so this is the way you can say have at the output an average value of the voltage VAN that basically say as this kind of coding. Okay, you are coding your information of the modulating signal into the variation of the duty cycle. Okay. These can be also regarded as a sampling of the control voltage. Okay, you are sampling your control voltage every TS. So this is a sampling process having as let's say sampling period the same of the switching period TS. Okay, this is the sampling period. So you should remember from communication theory that if you want to, let's say, reconstruct your original signal from a sampling process, then the bandwidth of your say signal to be reconstructed should be less than the frequency of your sampling frequency. Okay, 1 over TS. So it means 1 over TC. That means that if you could call B the bandwidth of B control of the modulating signal, this should be B should be less than, let's say, FC over 2 or Fs over 2. Okay, Nyquist. So all this discussion that I illustrated here made possible to recover the information correctly on the basis of this process, but we have a constraint. The constraint is that the bandwidth of this control signal should be well less than of your, say, switching frequency Fs. Okay, so it means that you need a control voltage that has variation that are very slow with respect to TS. If this happens, okay, so if the Nyquist theorem is valid, is say, respected, then this process, okay, is correctly explained in the way I did you before. Okay, so if this process is correct, it means that you have a circuit in which the voltage VIN is K pole multiplied the control voltage. And K pole, remember, is VD over. Remember what are our constraints. First of all, one linear pulse width modulator. What does it mean? That the dynamics of the control voltage is inside the dynamic of the triangular voltage. Sometimes this can be expressed by using a coefficient, say, parameter, which is called amplitude modulation factor. MA. MA is the ratio between, let's say, the dynamic of the control voltage divided the dynamic of the triangular peak. Peak control voltage, let me call peak to peak. Okay, so say the dynamic of what? This MA in the linear pulse width modulator is less or at the maximum equal to 1. Okay, so linear pulse width modulator as a direct, say, expressions if you use this parameter, which is called amplitude modulation factor. And the second constraint is that you need a bandwidth B of the signal you are, say, considering as a control valve modulating signal, which is less than half the switching frequency you are using. Typically, this is well less, okay, because the modulation process can be made more easy, so can be made easier if you have the possibility to have B well less than the switching frequency. Okay, the filtering action at the output, the low pass filter you can use as a demodulator operates, say, in a better way if B is well less than Fs. Okay, so you have these two constraints. So this means that, for example, since this is a classical, let's say, amplification relationship, you can have, I don't know, this is our modulator, okay? Then you have your modulating signal. The modulating signal can be this one. This can be, for example, I don't know, just for an audio track of your preferred singer, I don't know, per jam, which is mine, for example. Okay, this is an audio track, is a signal. Okay, the bandwidth hit, say, at the most 22 kilohertz. If you are using TS, which is higher than 22 kilohertz, I don't know, 100 of kilohertz, for example, then you can use this process to generate an audio amplifier. Okay, so it can be employed for our audio amplifier. There exists audio amplifier that are based on this switch action, on the basis of the K-pole. They are called class D amplifier. For example, you are acting in a linear region of the pulse width modulator. You use this process for modulating your, say, input signal, and then you can use, say, the modulation, etc. Okay, so it means that you can have, for example, also linear application of a sort of switching power converters. Okay, it seems to be strange to use something which is not linear, okay, in their operating principle to generate something which is basically a linear amplificator, but it can be done. The class D audio amplifier is exactly made in this way. Of course, this is not the topic of this course because I want to just use this switching power pole just for, say, driving electromechanical actuators. So typically what happens is that in our driving applications, okay, the control signal is not whatever, say, signal you can have in mind, but typical or is a DC quantity. Okay, I do at the beginning of this lecture, for example, for controlling, for driving DC motor, okay, or it can be a sine wave for AC motors, for example. Okay, so this is what happens typically in our driving application. So let me just focus a little bit on the situation in which you have as a control signal a sine wave. Okay. Suppose that this is our sine wave here. Okay, my sine wave has a period which is not exactly, say, much higher than the switching frequency. Is not respected Nyquist, my drawing. So it means that my sine wave should be very, very slow. Something like this, okay? And so what does it mean? That my duty cycle of QA is slowly modified in order to have a variation, which is the variation of a sine wave. Okay, when the sine wave is in the rising part, in the upper part, the duty cycle should be large. Then when the sine wave is in the lower part, the duty cycle is lower, etc. So the modulation of the unitary switching function follows a sine pattern exactly as the control voltage here. Okay, this is what happens. Now, this is a sine wave modulated rectangular waveform, okay? And here you have the spectrum of the voltage at the output. Typically, this is VAN frequency components, DC value, okay, DC value is K pole multiplied B control. Then you can have F1. F1 is, let's say, the frequency of the modulation, of the control signal. So suppose that my sine wave has a period, which is this one, T1. Okay, so 1 over F1. This is Fs. So this is the harmonics you can find for F1. This is the moving average that you can find at the output, okay, here, because this is sine wave modulated with a sine wave having frequency F1. Then you can have the fundamental component of the triangular carrier signal at frequency Fs. Then you can have harmonics, okay? And then you have something that appears that are intermodulation products, like this. You have some side bands. Okay, the difference here between the different lines is exactly F1. So you have the difference is always F1. So F1 is the frequency of the sine control voltage here. And then you have all these intermodulation products. This is called, let's say, here and here, that are side bands due to intermodulation products between, say, the harmonics of the sine wave at frequency F1 and then of the triangular waveform at frequency Fs. The frequency here are indicated like Fh. H is the number of this harmonic, is K1 Fs plus or minus K2 F1, where K1 and K2 are integers, and then you have this kind of description. So you can see here the output spectra is a little bit, say, complicated, okay, is full of harmonics and etc. Of course, here there is always the possibility to demodulate the signal using, for example, a low-pass filter. And if you use a low-pass filter, it is possible, for example, just to isolate these two, say, frequency components of the output spectra with respect to all high-order harmonics. Okay, I can skip all high-order harmonics around Fs or around 2Fx, etc., in order just to have at the output as average value a DC component plus a frequency which is the same frequency of the control signal. Okay, for example, inverters that are switch power circuit that are employed to convert a DC quantity, the voltage VD at the input of the switching power pole, to generate an IC wafer, so a sine wave at their output, are exactly fabricated or built exactly using this concept here. Okay, so just say with the same process as I indicated before, isolating what is I'm interested. Of course, this demodulation process is made easier if you are able to, say, reduce a little bit the quantity of these intermodulation products. As we'll see in future lectures about the inverters, most of the modulation techniques will be devoted to, say, reduce the number of the intermodulation products or the high order harmonics. Okay, so there will be some, say, specific techniques by which I can modulate the control signal in order to, for example, eliminate some of these intermodulation products, etc., in order to make easier the filtering of what I'm interested in. So, for example, the frequency F1. Okay, this is done. So this is something that we can study later. For this situation that is common for inverter applications, so for driving AC motors, remember that we have the amplitude modulation factor, which is now the V control A peak to peak versus the peak value of B triangular. And for linear application, this is less than 1. But here you can also define what is called the frequency modulation factor. Which is the ratio between the switching frequency and the frequency F1 of the sine wave you are using for control signal, as a modulating signal. Okay, frequency modulation factor. This frequency modulation factor should be well higher than 1 because we have to respect the Nyquist. Okay, so MA is less than 1, so we have what is called the linear pulse width modulator. Pay attention that sometimes in inverter application, some, say, inverters will exploit also non-linear pulse width modulator. For example, situation in which MA is a little bit higher than 1, what is called the over-modulation. Is done for specific purposes that we learn later in this course. Okay, in that situation, if you have again our modulating process graphically represented, then you can have something like this. You have the sine wave, the modulating signal that has, I don't know, behavior like this one. Okay, so as you can see here, there are some situations in which the control, the comparison, sorry, between the control signal and the triangular signal is correct. Like, for example, here or here, etc. But there are regions in which the control voltage is higher than the triangular voltage, like, for example, here, for all this region here, or for this region here, in which you have no more the possibility to, let's say, compare. The duty cycle is always 1. There are some specific reasons to exploit also overmodulation. Okay, if you want to use the switching power for linear audio application, like class D amplifier I said before, basically you have to operate in the linear pulse width modulator. But overmodulation can be exploited in inverter. Okay, basically inverters operate in linear pulse width modulator, but sometimes, and I will spend a very few words about this possibility, you can have also inverters that are exploited in overmodulation. Just to conclude this discussion, just a few words about the specific triangular waveform I can have in application like, for example, driver for motors. Okay, as I said before, it could be very important to make reasoning about the output spectrum, the voltage at the output, okay? Because it can be, say, complicated. It can be also complicated too much, the modulator, okay? Typically, a situation that you can have in a motor application, driving motor application, is that you want to, let me go to this slide here, okay? I said you have to put the modulator here. This demodulator, that also include L, acts as a low-pass filter in order to get what I'm interested in, okay, which is something very close, let's say, into the origin of the axis between the DC part or DC plus, say, the frequency F1 in case of sinusoidal control voltage, okay? This action in motor application typically is performed by exploiting the reactive characteristic of the motors. So that means that here I typically do not add nothing. I have a motor connected at the output. The motor has some capacitive and reactive, say, characteristic, resistive. Then typically the modulator is relies on the reactive parasitics of the motor. Okay, so in order to do that, in order to exploit this characteristic, since typically I don't want to add other filtering elements, etc., I need the spectrum at the output that should be very clean. I don't want to have, say, too much harmonics, because this filtering maybe is not effective, the filtering made by using parasitics of the motor. So in this sense, it is quite helpful to use a modulator that, by, say, just mathematically induces a spectrum which is, say, not too much complicated. This reasoning leads to for this kind of application, the use of a carrier signal, so this triangular wave, which is exactly done as in this way. So what is called the double edge triangular waveform. Why this leads to, say, a spectrum which can be less rich of harmonics, okay? Because if you have this situation, you have the triangular waveform, then you have your control signal, which is a very slow, it is not fast because the bandwidth should be less than Ts. Okay, so you can say that the output unitary switching function that is obtained by the standard process I explained to you before, basically the width of each pulses, here one, is modulated, is changed according to the variation of the control voltage by modifying both the position of the rising edge and the falling edge. Okay, these 2 points, okay, that change according to the variation of the blue curve, the control voltage. So for the comparison, both the rising and the falling edge are, say, modulated. Since the frequency of the blue curve should be very less with respect to Ts, this point here, for example, the point A and the point B, more or less are at the same level. It's not possible to have, for example, something which is, let's say, something which is, let's say, something like this, having this large variation, because this brings a bandwidth which can be larger, okay, larger than, say, 1/Ts. So this is not possible. By definition, I have to consider that this variation is very small. Okay, so it means that I modulate the pulse width modulation by changing the position of the rising and the falling edge, and this comes to be symmetrical about the point Ts, even here, and even. So this kind of symmetries that more or less you can have with double-edged triangular waveform is exactly the meaning by which the output spectrum of the voltage VAN is, let's say, among the other possible solutions, the less rich of harmonics. Okay, and this can help in demodulating by using simple filters. Okay, the situation is not is a little bit complicated if you are using what is called, for example, the trailing edge. The trailing edge is a pulse width modulator in which you have no symmetrical triangular waveform. You have something like this. Okay, the action of the modulator is performed in the same way. There is no variation like before. Okay, you have the triangular waveform, which is this rectangle triangle that you have the control voltage. If you look at how QA is generated, now you can see that you have something like this. Etc. So what you find that there is the possibility to modulate the width of the pulses, of course, because it's the basic of the pulse width modulation process, but you are modulating just this falling edge, this one, because the other, the rising edge, is fixed, because this, say, triangle is, say, instantaneous in this action. Okay, so here this point is fixed. You cannot move this. You cannot move this, you cannot move this, you cannot move this. Okay, you are just modulating the falling edge. Okay, previously you are modulating both rising and falling edge basically in a symmetric way with respect to TS. Now this sort of symmetry is totally lost. Fourier always likes symmetries in making, say, simplifying the spectrum. So this leads to some, say, complication of the spectrum, which is a little bit richest of harmonics. Okay, this is the basic reason why nowadays double edge is employed in place of trailing edge. Okay, and you have also the what is called the leading edge. Leading edge is a triangular waveform, okay, in which you can use in your pulse modulator that has this behavior. Okay, so in the leading edge, you can replicate all my discussion that I have for the trailing edge. Now, what happens is that you can change just the rising edge and not the falling edge, because the falling edge is fixed in time. Okay, due to this steep variation. The final consideration that I can have that pulse width modulation, so the modulation by which I have fixed TS and modulate the width of the pulse to modulate T on, is not the only possible solution. There exist some other modulation techniques. For example, you can make constant T on and modulate the frequency. Okay, this is exactly the same situation. You change the switch in frequency, but always have the same T on. Okay, this is also called pulse frequency modulation. Pulse frequency modulation can be employed, but again, there are a lot of problems. Okay, because the switching frequencies changes, and this is not something that we can, say, afford for our circuit, because, say, it is very, for example, filters that you can have at the output for the modulation can be a little bit more complicated. Also, EMI filters can be a little bit complicated for compatibility. And then there is many other modulation techniques for random modulation, let's say chaotic modulation, density modulation, etc. There are typically for, say, communication channels that can be employed also here. But I have to say that most of the time, 99% of the time, if you are not requiring some specific and particular situations in application, pulse width modulator is what you can find in your application. Okay, so sorry for having this extra delay here, but we are on time. If you have questions, I can answer now. If you have no questions, look at your student page for my message about the lab and reply saying me, yes, I'm available for all the 3 weeks, okay, starting from the beginning of May, or if you are not interested, you have not needed to reply, and we can see each other tomorrow at 11:30. See you. Thank you.